In this video, we're going to do some applications of the normal distribution. So in previous videos, we talked about how we could find areas underneath the curve given a z-score or two as a boundary, and we use the z-score chart to look up those areas. We're going to build on that. We're still going to find areas with these kinds of problems, but with these problems, oftentimes we're asked to find the probability of something or a percentage, and that's really synonymous with find the area under the curve. So if you have an area underneath the curve, that is the same as the probability of a value being in that area. It's also the same as the percentage of values that are in that area. So when you see those words probability and percentage, just think, okay, I've got to find the area underneath the curve. The other thing I'm going to mention is that with these problems, oftentimes, you're given information with real world context. So the information is not going to be set up for the standard normal curve where the mean is 0. And so we're going to have to find z-scores before we find any areas. So let's just jump into this first example and I'll show you what I mean. So the annual rainfall in a certain region is approximately normally distributed with a mean of 33.5 inches and a standard deviation of 5.6 inches. What percentage of years will have an annual rainfall of less than 30 inches? So the first thing that I like to do is I like to draw a picture. Probably not a surprise. We draw pictures for most of these problems in this section. And normally, a lot of times with the standard normal curve, I put a 0 in the middle. But since this problem gives me a mean of 33.5, I'm going to put that in the middle, 33.5. So this is not the standard normal curve. This is a normal curve that is showing the example data that I have here. And then we're asked to find the percentage of years that have an annual rainfall of less than 30 inches. So I'm going to draw a line where 30 inches would be, and I'm going to put it to the left of 33.5 because 30 is less than that number. And if I want the percentage of years that have an annual rainfall of less than 30 inches, then that means less than 30 means to the left. So I'm going to shade everything to the left. So really what we have here is we have a picture similar to pictures we've seen before, where we want to find the area. It's offset from the mean, so this is going to be a subtraction problem, but we need to, in order to find, use the z-score chart to find the area between 30 and 33.5, because the chart can give us that area. We need to find the z-score for 30 because that chart is not going to give us an area for 30. We need to know that z-score. So the first step is to find the z-score. So I'm going to use the formula z equals the data value, which is 30, minus the mean, 33.5, divided by the standard deviation, which is 5.6. And then make sure when you put this in your calculator, you either put parentheses around the top or you just enter it 30 minus 33.5, enter, and then divided by 5.6. And then when we do that, we get a z-score of negative, which you would expect since 30 is on the left of the center, 0.625. Now on the chart is all of the z-scores are rounded to the hundredths place. So we're going to round this since the chart is not going to even have a z-score of 0.625. So I'm going to round this to the hundredths place, 2 decimal places. So approximately negative 0.63. So that's the z-score that's associated with a rainfall of 30 inches. So I'm now going to look up on the chart a z-value of 0.63, and I've already circled it here. It's an area of 0.236. So I'm going to come back to my picture. This area right here is 0.236. So all of this that I'm kind of shading in red here is an area of 0.236. I don't want to know that area. I want the percentage that's left of, the 30 line. And so what I'm going to do is I'm going to, notice that, well, the entire left-hand side, we know that the entire left side has an area of 0.5. So if I just take 0.5 or 0.500, okay, that's the whole left side, and I subtract 0.236, which is what I don't want or don't need, because, you know, I don't need that area, I only need the part shaded in yellow, then that will give me what I do want. And so if I subtract those two numbers, I get 0.264. And then this problem asks for a percentage, so I can just take that area and move that decimal 2 spots to the right to get a percentage of 26.4%. And so let's actually think about this. What this means, it means that 26.4% of years are going to have an annual rainfall of less than 30 inches. So we just use the normal curve and, you know, all of our skills of finding area to actually answer, you know, a real world, you know, problem. So let's look at B. So B asks for the percentage of years that'll have an annual rainfall between 28 and 40 inches. So I'm going to do the same thing I did above. I'm going to start by drawing a picture. I put a line down the middle, which has the average, and then a line for 28 and 40. So 28 is going to go on the left because it's less than 33.5. And then 40 is going to go to the right because it's more than 33.5. And then I want to find the area between. And when we want to find the area between two values, where they are on either side of the middle, all we have to do is use the chart to look up the area here and then the area on the right hand side of the middle, and then we can add them together. So I am going, well, and let me stop for a minute. I need to use the chart, but the chart isn't going to have areas for values of 28 and 40, so I need to find the z-scores for those. So I'm going to do that first. So to find the z-scores, I'm going to first do it for 28. I'm going to take the data value, 28, minus the mean, 33.5, divided by the standard deviation of 5.6. And when I do that, I get negative 0.982. My chart only goes to 2 decimal places out though, so I'm going to just say approximately negative 0.98 for that one. And I'm going to label it on the chart. So this line right here has a z-score of negative 0.98. And then my other z-score, 40, so 40 minus 33.5 divided by 5.6. And that gives me a z-score of 1.1607, and I want to cut that off at 2 decimal places, which would be right here. So that would be approximately 1.16, and I'll label that next to the 40, so z equals 1.16. So now I'm going to look up on the chart z equals 0.98 and z equals 1.16. Remember that when z's are negative, we just look up the positive version on the chart. So a z-value of 0.98 gives me an area of 0.337, and a z-value of 1.16 gives me an area of 0.377. So you got to really be careful on ones like these, just not to mix up those numbers since they're so similar. So I'm going to come back to my problem, and I'm going to label those areas. So this area on the left here is 0.337, and the area on the right is 0.377. So total altogether, the area is going to be 0.337 plus 0.377. So I'm adding those two areas together, and I get a total area of 0.714. You can put a 0 in front of that too if you'd like. And then since the question asks for the percentage of years, I'm going to move that decimal 2 spots to the right, which gives me 71.4%. So 71.4% of years are going to have an annual rainfall between 28 and 40 inches. So now let's look at example 5. So we have the patient recovery time from a particular surgical procedure is normally distributed with a mean of 5.3 days, standard deviation of 2.1 days. There are 900 patients who go through this procedure this year. How many of those patients are expected to spend less than 2 days in recovery? So I'm going to start by drawing the normal curve. Put a line in the middle. Because they give me the mean, I'm going to put that in the center. And then our question, how many of these patients are expected to spend less than 2 days in recovery? So I'm going to put a line where 2 would be. And since 5.3 is in the middle, I'm going to put the 2 to the left of that, since 2 is less than 5.3. And so If we want to know how many of those patients are expected to spend less than 2 days, then really what would be helpful is to find the area to the left, because this represents less than. And that would give us an area or a percentage. And once we find the percentage, we could actually figure out the number of patients after that. Now, in order to find this area, if I'm going to use the z-score chart, is I have to know the z-score for 2. So I'm going to find the z-score for 2. So I'm going to take 2 minus the mean divided by the standard deviation, which they told me was 2.1 days. So I put that in my calculator and I get negative 1.571. The chart goes to 2 decimal places, so I'm going to kind of cut it off at the 7 and say the z-score is approximately negative 1.57. And so I will label 2 has a z-score of approximately negative 1.57. So now I can go to the chart, and you can see here I've already have it circled. A z-score of 1.57 gives me an area of 0.442. So I'm going to go back to my problem and label this area here. So remember, the z-score chart gives us the area between the z-score and the middle, 0. And so you can think of 5.3 as a z-score of 0. And so that area is 0.442. Well, I don't want that area. I want this yellow shaded area on the left-hand side. And so what I'm going to have to do here is have to subtract, knowing that the entire left-hand side of the curve, so the whole left side, has an area of 0.5. So if I subtract 0.442, which is this area that I don't need, then I can get the area that I do need. So I'm going to take 0.5, or you can do 0.500, minus 0.442. So we're going to subtract those and we get an area of 0.058. And then what we can do is we can find that's really a percentage. 5.8% would be the percentage. And if we wanted to find 5.8% of all of the people, so we have to look in the problem. Remember, there are 900 patients. So we need to figure out that what is 5.8% of 900. Well, we can just take the decimal equivalent, which is 0.058 times 900 people, and that, if we put that in our calculator, we get 52.2. Now they ask us about patients, so it doesn't make sense to have 0.2 of a patient, so at this point I would just round to the nearest whole number, which would be about 52 patients. So about 52 patients are expected to spend less than 2 days in recovery. And just to review here, the reason that we didn't stop at 0.058 is because it didn't ask for the percentage or area. It asked specifically for how many patients. And another clue is when they give you the total number of people in the problem, usually you're going to have to use that number. Not always, but sometimes. So in this next part, in part B, we want to know how many of those patients are expected to spend more than 2 days in recovery. And so we can draw the curve again with 5.3 in the middle. We can put a line where 2 would be, similar to what we did before, but now we want to know more than 2 days. So I'm going to shade everything to the right of 2 since it says more than 2. And the nice thing is I already did some work in the last problem. I already found that the z-score was negative 1.57, so that's nice. I already found that this area right here is 0.442. I know that the area to the right is 50%, which is the same thing as 0.50 or 00 as a decimal. So if I want to find that total area, all I have to do is add 0.442 plus 0.500. So I add those together and I get 0.942. But I don't want the area or the percentage of patients expected to spend more than 2 days. I want to know how many. So I am going to multiply 0.942 times 900 patients. And when I do that, I get 847.8. And so I'm going to round to the nearest whole number since we're dealing with people and we don't have a fraction of people or a person. So I'm going to just say 848 people or patients are expected out of the 900. So most of them are expected to spend more than 2 days in recovery. And then we've got one more. So in part C, how many of those patients are expected to spend more than 10 days in recovery? So I draw my graph. 5.3 is the average, the mean. I put the 0 on the top. That's equivalent to a z-score of 0. So 10 days would be more than 5.3. I'm going to put it on the right. So 10 days would be down here. I don't know what this z-score is, so I'm going to find that z-score before I do anything else and try to look up my area. So I'm going to take the data value, which is 10, minus the mean of 5.3 divided by the standard deviations, which was 2.1, was given in the beginning of the problem. And so when I put that in my calculator, I get 2.238. It's a long decimal, and so I want to cut that off at 2 decimal places. So that's going to round to 2.24. So that's the z-score of 10. And so now I'm going to look up on my standard normal distribution chart a z-score of 2.24, and you can see it has an area of 0.488. So I'm going to come back to my problem and label this right here, area, is 0.488. So the chart always gives me the area between 0 and then the z-score. And so I don't want this area that the chart just gave me though. I would like more than 10 days. So we're looking at this area right here. And so since I want that area, what I can do is I can take the area of the entire right side of the curve. So the entire right side of the curve is 50%, which has an area of 0.5 or 0.500. And if I subtract the section that I shaded in red, the 0.488, then I can get the section that's shaded in yellow, the more than 10 days. So I'm going to take 0.500, the entire right-hand side, and I am going to subtract 0.488. This is what I don't need. And that's going to give me what I do need. And so when I subtract those two numbers, I get 0.012, which is 1.2%. And so I look back to the problem to see, well, what kind of answer do I need? Well, they want how many of those patients. So I'm going to take 0.012 and multiply that by the total number of patients, which is 900, because they're asking for how many, they're not asking for a percent. So when I multiply that, I get 10.8. And then because we're dealing with patients here, we're just going to round that to the nearest whole number, which is about 11. So we say about 11 patients out of 900 are expected to spend more than 10 days in recovery. So not super common. Okay, so we have one more example. In example 6, suppose that the distance of fly balls hit to the outfield in baseball is normally distributed with a mean of 250 feet and a standard deviation of 50 feet. If one fly ball is randomly chosen from this distribution, what is the probability, so hint area, think area when you're asked for probability, that the ball traveled less than 200 feet or between 305 and 345 feet. So let's first sketch the graph. I'm going to put the mean of 250 in the middle. And remember, this has a z-score of 0. And we've got a standard deviation of 50. And so they're asking me, what's the probability that the ball traveled less than 200? So I'm going to draw a line where 200 might be. That would be less than 250. So I draw it to the left. And since it's asking less than that, I'm going to shade everything to the left of that. So the probability of being in that region, or between 305, so I'm going to put 305 over here, since it's greater than 250, and 345. And so I went between those two numbers, okay? I don't know the z-scores for any of these, so I'm going to have to find those. That will be my first step. The other thing to note is that we've got two different areas here, so we almost have to treat this as two different problems. So I'm going to first start and just find the z values for all of these, and then we'll go ahead and approach the areas after that. So for 200, I'm just going to go from left to right. So I'm going to take 200 minus the mean divided by the standard deviation of 50. When I do that, I get -1. So that has a z-value of -1, one standard deviation below for 200 feet. And then for 305 feet, 305 minus the mean divided by the standard deviation of 50, I get 1.1. Okay, so that's the z-value for 305. And then for 345, I minus 250, I divide it by 50, put that in my calculator, I get 1.9 for that z-score. Okay, so now I'm going to look at the z-score chart and find the areas associated with all of these z-scores. Okay, so I bring up the area under the normal curve chart, and it looks like for 1, I have an area of 0.341, 1.1, which is the same thing as 1.10, I have an area of 0.364, and then for 1.9, I have to scroll down a bit. That's also 1.90, has an area of 0.471. So I jot all those down and then I label my picture. So remember that the z-scores that the chart gives us are always between 0 and the z-score. So the area that was associated for 1, for -1, which is the same thing as the z-value of 1, is 0.341. Okay? And then for 1.1, so that would be this area from between 0 and 1.1. So that was 0.364. And then from 0 to 1.9, so this entire area, this would have an area of 0.471. So I'm first going to just look over here. We'll say this is part 1. So for part 1, what I'm going to do is I'm going to use the fact that the entire right-hand side, the area is 0.50 or 0.500. So this is the entire, I said right, I meant left, sorry. So left side, so the whole left side is 0.500 or 0.5, 50% of the curve. And we know that 0.341 is the area of this area right here that I don't want. So I'm going to subtract 0.341 to get that yellow shaded region, which I called part 1 on the left hand side. So if I subtract these two numbers, I get 0.159. Okay, so that's this area on the left here. Okay, and then for part 2, I'm going to need to subtract these areas. So 0.471 is this entire area here. Well, I don't want that whole area. I want to take off this white section that's labeled 0.364, and that will give me this yellow shaded section here on the right hand side. And so if I subtract these two numbers, I get 0.107, and that's going to be my part 2 number. That's the area of the shaded region on the right hand side, 0.107. And so in the end, if I want to know the probability that it's going to be in either of these regions, I'm going to add them together. So we're going to add the two sections, the two shaded areas together. So we're going to take 0.159 and we're going to add 0.107, and we get 0.266. And so we could even think of that as a percentage as 26.6%. So what is the probability that the ball traveled less than 200 feet or between 305 and 345 feet? Well, it's 26.6%, or as a decimal, 0.266. And then we have one more follow-up question. So this question asks, in what percentile is a ball that travels 220 feet? So a percentile, that just tells us the percent below or less than a certain value. So if we're looking for the percentile of 220 feet, I'm first going to draw a line where that would be, and since it's less than 250, I'm going to draw it to the left. So I'm going to label this 220, and since I want the percentile of that number, I'm going to find the area to the left of that, since percentiles always represent the percentage below a certain value. So below is associated with shading to the left. And so I don't know what this z-score is, and I need it to find that area, so I'm first going to find the z-score for 220. So I'm going to take 220 data value minus the mean of 250 divided by the standard deviation of 50, which was given at the beginning of the problem, and I get negative 0.6. And so I'm going to look up on the chart 0.6 since the chart doesn't have negative values and it's symmetric, so 0.6 will give us what we need. And so looking that up, I get an area of 0.226. So I'm going to come back to my problem and I'm going to label. Remember that the chart gives us areas between 0, the middle, and the z-score. So this area right here is 0.226. So all of this right here. I don't want that area though. That is not my answer. I want this shaded region on the left-hand side. So what I'm going to do is I'm going to use the fact that the area of the entire left side of the curve is 50%, which means the area is 0.5 or 0.500. So I'm going to take 0.500 and I'm going to subtract 0.226, which is what I don't want. And then I'm going to get an area of 0.274. So that's the area of that shaded region. So it means 27.4% of the time the balls, well, a ball that travels 220 feet is going to be in the 27.4th percentile, but with percentiles we usually round to the nearest whole number, so we're just going to say this is about the 27th percentile.